This is a magic triangle, and the reason why it is so magical is because of how easy and at the same time how accurate it can be for us when we are trying to calculate for distances in a vectors question related to our syllabus. It is actually a very simple triangle to understand because we will just be making use of what we have already known about a right-angled triangle in our secondary school. So if we were to have the hypotenuse as r, if I have the angle there as theta, then the vertical side, if you have to go through sine theta is equal to y over r, then the vertical side is r sine theta. And the horizontal side of this triangle, okay, the one that is based on this triangle here, the horizontal side is going to be r cosine theta. So it is very easy to understand, but to have it as something that is magical for us so that it can be consistently, easily and precisely helping us to find distances in a vectors question. Let me try to show you on the board here using an example. Let's say we have this vector here as A and we have this vector here. This vector here is B. And if I were to try to find the length of projection of A onto B, which means that we are supposed to be finding this distance here. So in order for you to find this distance, the first thing that we are supposed to do is to be able to visualize the scenario, which I've already just drawn here, and we can see, we can visualize that this is the distance that we are supposed to be calculating. So the magic triangle provides us an interface between what we can visualize and the kind of math rules and math equations that we can be using that is related to vectors. So if you are to look at this, the first thing that I'm going to try to do is to try to find the magic triangle that is in this scenario. And I don't think it is that difficult to guess which one is going to be the magic triangle. If I were to look at what that is there, the three reded colored part are the three qualities of a magic triangle. So the first thing is we have a right-angled triangle. And the second thing will be for us to be able to have an idea of the hypotenuse. Okay, in our case here, this is the hypotenuse, and the idea that we have for the hypotenuse is that its magnitude is 8, since A is a vector that is given to us. But theta is the one that I personally find is what that makes this triangle magical when it is being applied for us to solve distances question in vectors like this. Because theta, if you think about it, there are actually two possible places to position theta. Okay, it can be here, it can be here. I will still be able to use what we have learned in our secondary school. But the thing is, we are going to be bringing in vectors equation. And it is actually going to be dot and cross product. So if I were to think about dot and cross product, they actually involves the angle that is between two known vectors, right? So theta, when I'm trying to assign it to my scenario, I will always make sure that I will assign theta to be the angle that is between two known vectors. I know this vector, I know this vector, so I'm going to be assigning theta here. This is going to be theta. Not here, because we have this vector, but we don't have anything that is along this. Okay, that is why theta is supposed to be here. Then, by making use of what we have learned in our secondary school, we know that this length here is modulus of A cosine theta. And because we have chosen theta to be the angle that is between two known vectors, and now we see cosine theta, I'm going to bring in the dot product, because dot product involves cosine and involves the angle that is between two known vectors. So looking at what I need to be calculating, bringing dot product, taking this and this, it will be A dot B. And A dot B is equal to modulus of A, modulus of B, cosine theta. And from this equation, we can actually have modulus of A cosine theta, and it is here, modulus of A cosine theta. So modulus of B, which is a scalar quantity, I can just divide it across to the other side. So now we have an alternative way to calculate for modulus of A cosine theta, which is going to be equal to A dot B divided by modulus of B, which means what is the length of projection of A onto B? It is going to be A dot B divided by modulus of B. And because we do know that A dot B can be negative, okay, and we are looking at length, So I'm going to do an overall modulus to this. Similarly, if another day, another instance, we want to find this distance instead. Let's say this point here is A, and we are interested in finding the shortest possible distance between A to B. So the first thing that we will do is we will try to locate the magic triangle in our distance scenario, making sure that theta is going to be the angle that is between two known vectors. Then using our secondary school's calculations, we know this is going to be modulus of A sine theta. And because again, we have selected theta to be the angle that is between two known vectors. So now sine appears and theta, which is the angle that is between two known vectors, appear. We can use the cross product. Using cross product, specifically this modulus of A cross B is equal to modulus of A modulus of B sine theta. And for what we have here, we can see modulus of A sine theta, which is what we are trying to calculate as distance. So making this a subject, modulus of B, bring it over to the other side. We have modulus of A sine theta is equal to modulus of A cross B, B, bring it over to the other side, modulus of B. So what is the shortest possible distance from A to B? This distance is going to be modulus of A cross B divided by modulus of B. And one last thing, because both the numerator and the denominator, they are positive unlike this, so there's no necessity to put in any additional modulus notation.